Today's keeper is keeper 5.6, interpreting graphs. Alright, so this is almost like a review of what we already covered back in Unit 3 when we did our curve sketching, but we just want to look at it in a little bit more detail, make sure that we really understand what's going on from F to F prime and vice versa, or even to F double prime. So the first thing we want to talk about is critical values. So if you remember, your critical values is everywhere where your derivative equals 0 or doesn't exist. Those critical values are most often seen as maxes and mins of your original f of x function. So again, when you take that derivative, if your derivative equals 0 or if your derivative doesn't exist, we call that a critical number. Most people forget the does not exist part, so make sure you have that. Derivative equals 0 or derivative does not exist. So here's an example where they're asking us to find the critical values of x cubed plus 6x squared plus 9x plus 1. So to find this derivative, I'm going to simply use my power rule, and I get that the derivative is 3x squared plus 12x plus 9, and I'm going to set that equal to 0. Now, I don't have to worry about the derivative not existing anywhere because a cubic function, it has a smooth, continuous domain, and there's no, like, cusp or corners or vertical tangents or anything that I'd have to worry about. So I don't have to worry about that does not exist, but I do need to set that derivative equal to 0. So when I set this equal to 0, the first thing I notice is that it's all divisible by 3. So I divide 3 on each side, and I get x squared plus 4x plus 3. From there, I'm going to factor it to be x plus 3, x plus 1, and then I'm going to set my factors equal to 0 to get x equals negative 3 and x equals negative 1. Next, we want to find our intervals of increase or decrease. So your intervals of increase are intervals where your derivative is positive, whereas your intervals of decrease is the intervals where your derivative is negative. So using that same example that we just used in the first slide, we want to find the intervals of increase or decrease of the same function. So basically what I'm going to do is I'm going to take my critical numbers, I'm going to put them on the number line, and I'm going to plug numbers in to the left and to the right of my critical numbers into my derivative. That's the catch. I'm plugging into my derivative. Now, if you remember, your derivative was 3x squared plus 12x plus 9. That was a quadratic pointed upwards. So I know that to the left of 3, I know for sure that's going to be positive. And then I know in the middle I have a negative, and out to the right I have a positive by the rules of a quadratic. And so therefore by that I know that it's increasing from negative infinity to negative 3 and from negative 1 to infinity, and then it decreases from negative 3 to negative 1. Next we have our local extrema, or our max or our mins. Again, we're going to focus on our derivative, and where our derivative changes from positive to negative, I know I have a local max. Where the derivative changes from negative to positive, I know I have a local min. And we need to make sure we understand that the local max and mins, those extrema, those are y values. So if I say what is the extrema or what is the value of the max or the min, you're giving me y values. If I say where is the value of the max or the min, you're going to give me x value. You'll say it happened at x equals whatever. But again, if I ask just for the max or the min, you need to make sure you're stating those in y values. Alright, so same example, same f of x equals x cubed plus 6x squared plus 9x plus 1. I'm taking my first slide answers for those critical numbers, negative 3 and negative 1. Again, I have to remember that to the left of 3 was positive, to the right was negative, and then to the right of negative 1 was positive. Now, when I say it's positive, that means my function must have been increasing. And when I say it's negative, that means the function must have been decreasing. So around negative 3, I was increasing, and then I started decreasing. This looks like the top of a hill. Well, therefore, that's a max. And I can use the same logic to figure out what negative 1 is. I'm decreasing to the left and increasing to the right. So again, when I look at that, that looks like a valley, and therefore, that is a min. So f of negative 3 equals 1 is a local max, and f of negative 1 equals negative 3 is a min. Notice I got these negative 1s and these negative 3s by plugging back into the original function. So if I plug in negative 3, I'm going to get 1. If I plug in negative 1, I'm going to get negative 3. Alright, so next we're looking at our absolute max and mins, and we're still going to use our critical points that we found in the very first slide, but we also have to take into consideration our endpoints. And so basically what you're going to do is you're going to find the f of each of your critical numbers and the f of your endpoints. So I'm going to start with the leftmost endpoint, and I'm going to find f of negative 3. Again, I'm plugging into the original function, and when I plug that in, I get 1/8. Next, I'm going to find f of my leftmost critical point. So f of negative 3, plug that in, and I get that equals 1. Next, I'm going to find my rightmost critical point, which was f of negative 1. Plug that into my original function, I get negative 3. And lastly, I'm going to plug in my last endpoint, which was 0, and so I get f of 0, which is 1. And so that lets me know that my max is going to be 1, and my min is going to be negative 3. So again, f of negative 3 and f of 0 give me a max of 1, and f of negative 1 gives me a min of negative 3. Okay, now we need to talk about concavity. And if you remember, concavity deals with your second derivative. So to figure out if we're concave up, we want to know that the second derivative is positive. And whenever the second derivative is negative, we know our graph is going to be concave down. So again, using that same graph, I'm going to find my second derivative, and our second derivative will be 6x plus 12. I'm going to set that equal to 0, and I get x equals negative 2. Next, putting that on a number line and testing numbers, plugging into my derivative, into my second derivative. If I plug in something to the left of 2, like let's say negative 3, I get a negative number. And if I plug in something to the right of 2, let's say 0, I get a positive number. And again, remember, I didn't necessarily have to do that because I knew my second derivative was a linear function going up from left to right. So on the left you have negative, on the right you have positive. Alright, so once I know that, I can figure out that I must be concave up from negative 2 to infinity, and then concave down from negative infinity to negative 2. Lastly, we have our points of inflection. Your points of inflection occur where your second derivative equals 0 or does not exist. So again, you still have to take into consideration where that function doesn't exist. It could be an asymptote, it could be a whole, it could be any of those values, but you still need to look into it to see if your function doesn't exist there. Now again, our second derivative exists everywhere because our second derivative, again, was continuous. It was a linear function, so I don't have to worry about the does not exist in this example. But I do need to set that thing equal to 0 and then figure out if it is an actual point of inflection. Remember, when you set it equal to 0 or you figure out where it doesn't exist, that's your possible points of inflection, not necessarily your actual points. You need to then check to see that whether or not it changes signs. So again, using the information from the last slide, we had the x equals negative 2 was what we got when we set our second derivative equal to 0. Again, from the left it was negative, and from the right it was positive. It does indeed change signs around negative 2. Therefore, x equals negative 2 must be a point of inflection. Now, to find the actual point of inflection, understand the word, it says point of inflection. You must have a point. So to find the y value of that point, you need to plug negative 2 into your original function. When I do that, I get negative 1, and so my point of inflection is negative 2, negative 1.